So of course we have to have exceptions. We've got a rule, there must be exceptions. One exception to the octet rule is odd-electron species. If you have a molecule or an ion that has an odd number of electrons, you can't follow the octet rule. These are called free radicals. They have odd numbers of electrons, so there's going to be one electron that doesn't have a pair. And that's going to be unstable, and so free radicals are very reactive. And that's why free radicals in your body are not a good thing, because they react with lots of stuff and they do things they're not supposed to do. So let's draw the Lewis structure for one of my favorite compounds. No! It's all caps, it's yelling, right? Okay. Yeah, get my own stupid jokes. 5 electrons and 6 electrons makes 11, right? Right? Yeah. 2, 4, 6, 8, 10, 11. That doesn't look very good. Well, we can't obey the octet rule. We're just going to do the best that we can. We're going to get lowest formal charges. So if we took a lone pair from this nitrogen and gave it to the well, not gave it, but shared it with the oxygen, that would improve things. Now this oxygen has an octet, and this one has 2, 4, 5. We can do better than that. Let's take another of these and share with the nitrogen and see how that works out. We got 2, 4, 6, 8, 2, 4, 6, 8, 9. Maybe not. Let's not do that. So we got 2, 4, 6, 8, 2, 4, 6, 7. So we can't get everybody to have 8. One's going to have 7. But we got 1 8 and 1 7. And we could have this odd electron over here, or we could give it to oxygen. Right? How do we choose? We're going to look at the formal charges. So for nitrogen here, remember what we're doing is we're cutting the bonds in half. Chop. Nitrogen brings in 5 electrons, and it leaves with 1, 2, 3, 4, 5. 0 formal charge. Oxygen brings in 6. Brings in 6, leaves with 2, 4, 6. 0. That's probably our winner right there. Let's look at the other one. Nitrogen brings in 5, leaves with 6. -1. Oxygen brings in 6, leaves with 5, +1. And that's the best Lewis structure for nitrogen monoxide. You can't make a perfect one, you just get as close as you can. Any questions? We also have exceptions where the octet is incomplete, meaning it has fewer than 8 electrons. And this is going to happen with some of the smaller elements. So boron, right? Boron is element number 5, one of the little guys. Boron will often violate the octet rule in this way. So let's draw a Lewis structure for BF3. It's like best friends times 3 or something. Let's put boron in the middle and the fluorines around it, because it's symmetrical and electronegative elements tend to be on the outside. And then we've got 3 fluorines. They each have 7 valence electrons. And the boron has how many? 3?
Yeah.
Well, so 3 times 7 is 21, plus 3 is 24. Pretty sure. Okay, 24. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now, we would like to take a lone pair from the fluorine and give it to the boron so that the boron can have an octet. But that's not what it does. Fluorine, as an atom, has one unpaired electron. Fluorine likes to make one bond. When it makes one bond, it has a zero formal charge. Boron has 3 valence electrons. They're all 3 unpaired. It likes to make 3 bonds. When it makes 3 bonds, it has 0 formal charge. Here we've got each of the fluorines with 1 bond, the boron with 3 bonds. All of the formal charges are 0. So even though this violates the octet rule, it is the correct Lewis structure. And if you want to cut these in half and do the math, boron brought 3, it leaves with 3. Fluorine brings 7, it leaves with 7, all zeros. Now, BF3 will tend to react with other things in a way that will complete the octet on boron. But BF3 does exist, and it has all single bonds. So boron often does this, and beryllium, another small one. And beryllium, you're like, but wait a minute, isn't beryllium a metal? Well, yeah, kind of. But it's one of the least metallic metals, and so sometimes it forms covalent bonds. So that was not enough electrons, less than 8. We can also have more than 8, right? If you're going to break the rule one way, let's break it the other way as well. So this only works with the bigger elements. So period 3 or larger. We often see expanded octets more than 8 electrons, up to 12 or even 14 electrons. That's a lot above 8. So let's draw Lewis structures for arsenic pentafluoride and sulfur hexafluoride. And we'll spare all of the gruesome details and just kind of go through this quickly. So I need 5 in there, and that's not fitting very well, so I'm just going to stick one at an angle here. Arsenic has 5 valence electrons, and, we better write this out. I'm going to do this in my head. We have 5 valence electrons, and we've got 5 fluorines that each have 7, and so that's, 40? So I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. It looks, well, it's a little bit weird, but it's symmetrical, isn't it? What are the formal charges on those fluorine atoms? Fluorine likes to make one bond. Does it have one bond? They all have one bond. The formal charges are 0 on all of those fluorine atoms. That's good. If we talk about, if we go through and look at cutting up the bonds and calculating the formal charge, arsenic had 5 valence electrons, so it brought 5 in, and if we cut all these bonds up, how many is it going to leave with? 5. 0 formal charges. Arsenic has 2, 4, 6, 8, 10 electrons instead of 8. What's up with that? Well, arsenic is in period 4. Arsenic has d orbitals. So it can expand into the d orbitals, and so it can take on more electrons than 8. The guys in period 2, you've got 2s and 2p. That can only hold 8 electrons. And so those are limited to 8. They never go above 8. But when you get into 3, there's 3s, 3p, and 3d. And like chlorine, sulfur, they don't have any electrons in the d orbital. But if some extras came, they've got overflow, they could put them in there. SF6, sulfur, and 6 fluorines. We can do the math. It's the right number of dots. What are the formal charges in? Fluorine we don't have to think too much about because fluorine likes to make one bond, and it's got one bond, so those are all good. The sulfur had 6 valence electrons, and if we break all these bonds in half, it's going to leave with 6 electrons, 0 formal charges. Both of these are stable compounds. They violate the octet rule. Any questions? H2SO4, sulfuric acid. Sulfur in the middle, 4 oxygens around, and there's going to be hydrogens on the oxygens. I would expect you to take longer to do that, but we don't need to do that in public. 2 times 1. So there's the hydrogens, the sulfur has 6, and we've got 4 oxygens, they each have 6. So that's 32. 24 and 6 is 30, and 2 is 32. So we've got 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Well, it's good. Does that obey the octet rule? Sure does. What about the formal charges, though? Sulfur is in period 3. Sulfur can take on more than 8 electrons. It can expand. So we have to consider that as a possibility. So if we look at formal charges, this oxygen brings in 6 electrons, leaves with 7. 6 minus 7, it's got a -1. This one is in the same position. This has got the same number of bonds and number of lone pairs. So that one's -1. This one, we cut those bonds. Oxygen brings 6, leaves with 2, 4, 5, 6. That one's 0. Hydrogen's always 0. This one's also going to be 0. What about the sulfur? Sulfur brings 6 electrons, leaves with 4, plus 2. And it's encouraging that we've got -1 and -1 and plus 2, and it adds up to 0. So what we want to do is we want to experiment with expanding the octet on that sulfur to see if we can get 0 formal charges. This being a positive formal charge means that this sulfur maybe doesn't have enough electrons. This oxygen having a negative formal charge means it's got too many. So what we want to take some electrons from this oxygen and give them to the sulfur. So let's do this. I'm going to, well, what am I going to do? I don't know what I'm going to do. We'll take off those and make that a double bond. The oxygen still has 8. What does that do to the formal charge on this oxygen? It's 0. Oxygen likes to have 2 bonds, now it has 2 bonds. So now this has a 0 formal charge. What's the formal charge on the sulfur now? It brought in 6, it's leaving with 1, 2, 3, 4, 5, plus 1. That's better, right? We've got this one over here with also too many electrons. So if we take a lone pair here and share it, we can make things better. Now that was a little too close. What's the formal charge on this oxygen now? 0. And on the sulfur? Also 0. That's better. 0 formal charges. And this is actually what it does. This sulfur has an expanded octet. And so it's got, what, 12 electrons? 2, 4, 6. Yeah, 12. But it's okay. It's in the third period. Third period, fourth period, fifth period, they can do that. Period 2 elements, never. They can't. There's no extra orbital for them to expand into. So sulfur's got people on the third floor, right? When it gets an octet, the S room's full, the P room's full. If more people come, well, we can put them in the D room. That's fine. For oxygen's people are on the second floor. There's an S room and a P room. The octet fills those up. Where are you going to put more electrons? You can't go up a floor. There's no more room. Done. Write the Lewis structure for XeF4. Well, let's put Xe in the middle. This is one of those weird noble gas compounds. Xenon has 8 valence electrons, 4 fluorines with 7 each. 4 times 7 is 28, and 8 is 36. Better write that down before I forget. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Excuse me. I get too many electrons. I've used up 32. I need to stick 4 more on there. Can fluorine take extra electrons above 8? Period 2. Nope. Can xenon? Yeah, xenon's in period 6. So I'm going to put those lone pairs on the xenon. Does it look weird? Yeah, it looks weird. What are the formal charges? Well, the fluorines have an octet and 1 bond. They're all 0. Xenon brought in 8, and if we cut these bonds in half, it gets 1, 2, 3, 4 from those. 5, 6, 7, 8. 0 formal charges. Bingo. H3PO4. This is going to be a lot like H2SO4. Put the P in the middle. We've got 4 oxygens. And the hydrogens are going to be on the oxygens. Now, let's think about this before we start putting the dots in. How many bonds does oxygen like to have? 2. This oxygen has 2 bonds. This one has 2 bonds. This one has 2 bonds. That one only has 1 bond. If that's going to have a 0 formal charge, there has to be a double bond there. So let's just try it that way. We've got 3 electrons from the hydrogen. We've got 5 from the phosphorus, and we have 24. 24, 29, 32. What was this? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So you can cut the bonds and do the adding and subtracting. Hydrogens are always going to be 0 formal charge. These oxygens each have octets and 2 bonds. Those are all 0. What about the phosphorus in the middle? Had 5 electrons coming in. and it would leave with 5, also 0 formal charge. So when you have an element that's in the 3rd period, 4th period, 5th period, 6th period, 7th period, and you draw a Lewis structure and you have formal charges, look at expanding the octet on that larger atom and see if you can get 0 formal charges.